Good day, ladies and gentlemen. I'm still Tumelo Athamohali, and then we are continuing with a new chapter today, which is hypothesis testing. So we'll be looking at a single population. So we will be making assumptions or making claims about a single population parameter, and then we'll be testing those claims about the population parameter. So, as I always do, it is very much important for me to highlight the most important things you should know in this chapter. Remember, after the successful completion of each chapter, you should be able to master certain things. So you need to know the information I am going to give you in order for us or for one to regard you as the master of hypothesis testing, the single population. So it is very important, ladies and gentlemen, for you to understand the concept hypothesis. I know you already know about hypothesis. You did hypothesis in biology, you did hypothesis in geography, you did hypothesis in many subjects you were doing in high school, and also certain modules you found here at university. So it is very much important for you to know that when we hypothesize in statistics, we hypothesize about a population parameter, or we make claims or assumptions about a parameter. And remember the difference between a parameter and a statistic. We said parameter goes with population, meaning that because parameter starts with a P and population starts with a P, then they go together, meaning that there's no way you can talk about parameter without talking about population. What I'm trying to say here is that parameter, as part of your revision, is a specific characteristic of a population. I'm gonna repeat. We define parameter as a specific characteristic of a population. For example, we can have a population mean. That population mean is a characteristic of what? Of a population. And then we have population standard deviation. Remember, we denote population mean with a mu. And then population standard deviation is sigma. So these are examples of parameters, or the population parameters, as one would say. Whereas when we talk about a statistic, it starts with an S, and then the sample also starts with an S, right? And these are from yes, as I was elucidating, I'm having connectivity issues this side. I can see my connection is unstable. So statistic is a specific characteristic of a sample. And remember, you draw a sample from a population, meaning that population is the collection of all items of interest, whereas a sample is the subset or a portion of a population. So we get a sample from the population. That is just a brief introduction to this chapter. But that is not really important for now. So what is important is what I'm going to show you now. Let me do this so that I can be able to present my board and you see where I'm writing. Let me share the screen so that we can make this live simple. Hmm? This is what I want us to do. Like I said, you should know that. You should know the definition of hypothesis. You should know how to define hypothesis. So when we talk about hypothesis in statistics, we talk about a claim, or you can say we talk about an assumption. So hypothesis is a claim or an assumption about a population parameter. A claim or an assumption about a population parameter. And I gave you examples of parameter. So we spoke about population mean, which is denoted by mu. And then we also spoke about population standard deviation, which is denoted by sigma. And then we can also talk about variance, which is sigma squared. So these are population parameters. And in this chapter, we are going to look at the population mean. We'll be estimating the population mean and also the population standard error or population standard deviation. So we define population parameter as a specific characteristic of a population. And we define hypothesis testing as a claim or an assumption about a population parameter. I hope that is clear. And the other important thing you should know, my dearest students, is that a hypothesis is divided into two. There are two types of hypothesis. We have what we call the null hypothesis, which is denoted by H naught. We also have this second type of a hypothesis called the alternative hypothesis, which is statistically denoted by H1. So wherever you see H naught, just know it's a null hypothesis, whereas H1 is an alternative hypothesis. So this chapter is very simple. So when it comes to null and alternative, H naught and H1, this is what you have to know. Because when you read a statement and then you also further read the question, you will realize that you are given hypothesis, but they will never tell you the type of hypothesis given there. It's very important for you to familiarize yourself with what we call the statistical jargon, as I used to say. So how do we identify, or how can one identify the null and the alternative hypothesis? So this is how you can identify those. Null hypothesis is denoted, okay, null hypothesis always has an equal sign. Make sure you write this somewhere. It's very important. A null hypothesis is that hypothesis that always has an equal sign, meaning that you can have equal to, you can have greater or equal to. You see, there is still equal sign there. And then you can also have less or equal to. And you know that equal to is the same as exactly. Greater or equals to is the same as at least or not less than. And then less or equals to is the same as at most. So I'm not going to revisit all those terminologies. So I taught you how to denote at least. Why is at least greater or equals to, whereas at most is less or equals to. Whereas in English, we know that if something, if we have most, it means that we have more of something, or something is in excess. But in statistics, it's a different story. So at most means less, as I used to say. So I'm not going to overemphasize it. So to get a better understanding of this, you can refer back to the videos I have uploaded in the previous weeks. So you will develop a better understanding of what I'm talking about here. So that's how we denote the null hypothesis, which is H0. And then that's how we can identify it. There's always an equal sign. This is equal sign. This is equal sign. This is also equal sign. That's why we are saying in null hypothesis, we always have an equal sign. So what about an alternative? The alternative is just the opposite of the null. The alternative is the opposite of the null. So meaning that if you are given equal to, the alternative for equal to is what? Is not equal to. What is the alternative of at least? I taught you. I said for you to identify the alternative, this is what you are gonna do. So you will say, okay, I need the alternative for greater or equals to. So I need to hide this equal sign here. You hide it, you can use your finger, then you will no longer see it. You act as if you don't see it. And then after hiding it, you will remain with what? With greater than. Very good. So you remain with greater than. So in order to get its alternative, you will change that sign. Instead of having greater than, we will have less than. So in other words, less than is the alternative or is the opposite of greater or equals to. So let me give you an example. Let's say we have greater or equals to 2. So it means that we need values that are equal to 2 or that are more than 2, meaning that we need values from 2 upwards. So you'll have 2, 3, 4 up to infinity, right? But then the alternative of greater or equals to 2, if we don't want greater or equals to 2, it means we will need less than 2, meaning that 2 is no longer included. So we'll take values that are less but not equals to 2, less than 2, meaning that you can take from 1.9 going down. So that's just a practical example I can give to differentiate between that alternative and its null. So the alternative for greater or equals to, or the alternative for at least, is less than, as I have said before in the previous chapters. And then what about the alternative for at most, which is less or equals to? So you are going to hide the equal sign, you pretend as if you don't see it, and then you change the remaining sign, meaning that you will have greater than. So I'm introducing you to this now. Never forget, because you will need them somewhere, somehow. As I have said, in the test or in the exam, they will give you information in words. So they will say at least, they will say at most, they will say exactly, they will say not more than, they will say not less than, they will say greater than, they will say more than. So you need to know the type of hypothesis given that particular question. That is why I'm starting by introducing you to the differences between the null hypothesis and the alternative hypothesis. Just a key highlight on the alternative hypothesis, which is H1, you must know that this one, there's no equal sign. Whereas this side, we have the equal sign, as you have seen in all these inequalities, right? So that is important. We denote the null hypothesis with an H0 and then the alternative with an H1. That is important. Are we together? So we are moving on. So an example might be the average sales in ABC store in the previous month were 12. The average sales in ABC store in the previous month were 6. So meaning that you have a mean being equal to 6. So they will give you a statement like this. You need to know whether it's a null hypothesis or it's an alternative. What type of hypothesis is this? By looking at the information I already gave you. This will be a null hypothesis. Very good. Why is it a null hypothesis? Because of the equal sign here. And then what will be its alternative? Its alternative will be mean is not equals to 6. So that's why I have said in the test or in the exam, they will only give you information in words. You need to identify the hypothesis you are given. We are moving on. So in this lesson, we are going to estimate a single population parameter, meaning that we are only going to look at the one population mean and one population proportion. So these are what we are going to look at. So what do you need to know again in this chapter? You need to know about the types of errors. We have type 1 error. We also have type 2 error, right? Now, what is the difference between these types of errors? Type 1 error and type 2 error. So this is the difference. When we talk about type 1 error in statistics, we talk about that error that involves rejecting the null hypothesis, which is H0, when it is in fact true. We reject the null hypothesis when it is in fact true. That is type 1 error. I'm repeating. Type 1 error speaks to the rejection of H0, which is your null hypothesis, when it is in fact true. And it is considered a very serious error in statistics. Why is that the case? This is because in using these practical examples, let's say, for instance, we are saying a majority of the government officials are corrupt. This is a claim. It's what I think. And if it's a claim, it's a hypothesis, right? So I'm saying majority of government officials are corrupt. We are not sure whether that is true or not, right? So if that statement is true or is a fact, and when we go to the court, we reject it, or let me start here. In this chapter, we always go with the notion that hypothesis is true unless proven otherwise. Are we together? So we use the notion of innocent until proven guilty. So you can't say, because I'm given this claim, so this claim is false. You can't just say it's false. You need to test that claim before you can make a decision, or before you can make an inference to say this claim is false. So in statistics, we use the very same notion of innocent until proven guilty. So the claim or the hypothesis is always true unless proven otherwise, through the steps I'm going to introduce you to in a few moments. So I was still explaining the type 1 error, which is considered to be a very serious error in statistics. We are saying this one involves rejecting a null hypothesis. You should know, very important, we always reject H0. Never ever find yourself rejecting H1. Yes, from the question or from the statement, they might give you H1, but there's no way we can reject H1. We always reject H0. Make sure you write it somewhere. We always reject H0. That is important. Yeah, I talk too much here. I was explaining the type 1 error, okay? We said majority of government officials are corrupt. That is a claim. So let's say I go to court and then someone is suing me. So I am being taken to court to account. And then when I go there, I know that what I'm saying is true, right? And I have a tangible proof of what I'm saying or what I'm claiming about. So majority of government officials are corrupt. But then the justice or the judge, rather, rejects that statement. He says that claim is not true. It's false. So meaning that they are rejecting the statement of saying majority of government officials are corrupt. And that statement is true, but then they are rejecting it. You see, they are protecting the corrupt officials by saying they are not corrupt, whereas they are. So this is a very serious error because you are sugarcoating. Eh? So you are rejecting the null hypothesis. You are saying, no, this is not true. You are rejecting it when that statement or when that claim is in fact true. You see, we are saying this is not true, whereas it is. I hope we are together there. Now, when it comes to type 2 error, when we talk about type 2 error, we talk about the one that speaks to the rejection, or let me say, it speaks to the acceptance. Instead of rejecting, we accept in type 2 error. you accept or you don't reject H naught or null hypothesis when it is in fact false, right? I will give a practical example. With type 2 error, we are failing to reject the null hypothesis when it is in fact false. Someone goes to the court, these women, there are some women who like accusing men of rape. So the lady will say, my husband raped me, whereas that is not true. And then the person goes to court, and then they are saying, yes, you man raped this lady, whereas that man did not rape the lady. You see? So in this era, we are failing to reject the hypothesis when it is in fact false. That statement is false. That man did not rape that lady, but we are failing to reject that hypothesis, or we are accepting that hypothesis. You see? So that's the difference between type 1 error and type 2 error. And then in type 1 error, we are talking about rejecting the null hypothesis when it is in fact true. And then type 2 error, you just change the wording there. Instead of rejecting from type 1 error, we are saying in type 2 error, not rejecting, right? And then instead of saying when it is in fact true from type 1 error, we are saying when it is in fact false. So if you know one type of error, you automatically know the other, because we are just going to change the wording here and there. And the other thing you should know about these types of errors is that the probability of type 1 error is given by alpha, whereas the probability of type 2 error is given by beta. That is very important. Are we together? So we are now moving on. I have already introduced you to hypothesis. We have defined hypothesis. We spoke about parameters. We have distinguished between the two types of hypothesis. We spoke about the types of errors up to so far. And then now we are going to look at, or let me rectify something. So in this chapter, we are going to look at these parameters. We are going to look at the population mean as one of the parameters. We are also going to look at the population proportion, which is denoted by P. So in this chapter, we are denoting population proportion with a letter P. Do you still remember that in the previous section, we were using P as a sample proportion and then pi as a population proportion? But in this chapter, we are doing things differently. P is denoted, I mean to say, sample proportion is P head, and then population proportion is uppercase P. I hope we are together. So this is population proportion, and then this is sample proportion. You have to know that. Yeah, we are continuing. So now I am going to introduce you to hypothesis testing. Hypothesis testing involves a series of steps. So you can use the traditional approach, which is the critical value approach to hypothesis testing, or alternatively, you can use the modern approach, which is the p-value approach to hypothesis testing. So it does not matter which one you use. So the p-value approach is very simple. I am going to introduce you to this one of the critical value approach. So it involves 6 steps, and you should know them by heart. These are the general steps for the critical value approach to hypothesis testing. So make sure you note them down. We have step 1. In step 1, we state H0 and H1. In other words, we are stating the null and the alternative hypothesis. That is step 1. And then step 2, what do? You decide on the significance level, which is your alpha. Remember, we spoke about confidence level when we were doing confidence interval estimation. Now we are talking about significance level. And I said significance level is alpha, whereas confidence level is 1 minus percentage. So in this chapter, you'll be given a significance level. So significance level equals that particular percentage they are giving you on the question or on the statement. So you take it as it is. You'll never go wrong. This is just a 1 mark for free, because you take that value from the question. They will say, test at 5% significance level that this claim is true. So meaning that you just say on step 2, alpha equals that particular percentage, and then you get your mark. Then step 3, okay, before I continue, we will be using 1% as significance level, 5%, what else? 2%, and also 10%. So those are the values, the significance levels we'll be using. We use those most of the time. So you should know this and make sure you note it down as well. I nearly forgot. So sometimes the lecturer might decide not to give you the significance level. So if they don't give you the significance level, what are you going to do? Are you supposed to cry in the exam room and say, no, this question paper is erroneous, it has errors? Are you supposed to do that? No, you are not. If you are not given alpha, you are going to use an automatic one, or the one that we refer to as a default alpha. If you are not given a significance level, you are supposed to use a default alpha, which is what? Which is 5%, or 0.05, because 5% is 5 over 100, then you get 0.05. So if you are not given significance level, they assume you know. So it's given, they just did not write it in a black or red ink. They wrote it on a white sheet with a white ink. And you know, like colors will befriend, and then you will not see, or you will not distinguish between the two. Yes, I hope we are together. That is step 2. And then what about step 3? What are you supposed to do on step 3? On step 3, you are gonna compute a test statistic. My connection is unstable. My connection is unstable. But let us continue. On step 3, you compute a test statistic. Remember the knowledge you have from that chapter of confidence interval estimation. We introduced you to the 2 types of tables, the Z table and the T table. And then you know when do we use a T table and when do we use a Z table, right? So that knowledge, never ever forget it, because you are still gonna use the very same knowledge to come up with the formula for calculating test statistic. So when it comes to test statistic, you might be estimating mean, right? If you are estimating mean, it means that you can use either a Z table or a T table. And you know when to use this, I taught you. And then I'm just gonna quickly rush to the formula for calculating this. So when it comes to t-testing, depending on the information given or depending on the parameter you are assuming or you are estimating or you are claiming about or you are thinking of, then these are the formulas you'll be using. So if you are using a t-table, you will have t equals x bar minus mu over standard error of the sample mean, right? And you know, let me just remove this. Standard error of the sample mean, when you use a t-table, is what? Is S over square root of n. Remember, we use t-table when n is less than 30. I'm just reminding you, I'm doing you a favor. And then we use t-table when n is less than 30 and when sigma is unknown. So that's what we have to know. If those 2 conditions are not met, you cannot use a t-table. That is why here you have S instead of sigma. You have S, which is the sample standard deviation. Why? Because the population standard deviation is unknown. Right? So that's the first formula. The second one, you can say Z equals X bar minus mu over standard error of the sample mean, S over square root of n. I will remind you, you use this one, when sigma is unknown, but n is not less than 30, meaning that n is greater or equals to 30. Isn't it that when it comes to t distribution, you use it when those 2 conditions are met. If one of them is not met, you automatically go to Z table. So meaning that you use this table now because sigma is unknown, but n is greater or equals to 30. You see? Or the third formula might be Z equals X bar, this is X bar minus mu over sigma over the square root of n. That's the third formula. So these 3 formulas are for estimating or assuming about a population mean. And then what about a population proportion? So test statistic will be given by Z equals, remember in proportion we only use one table, which is the Z. Whereas when it comes to mean, we use 2 of them depending on the information given. So you can say we use P head minus P over the square root of P1 minus P over n, or z might be p hat, which is your sample proportion, minus p, which is population proportion, divided by p hat 1 minus p hat over n. When do you use this formula? You use this formula when p is unknown. When population proportion is unknown, right? Whereas here, you use it when population proportion is known. I hope we are together. That is step number 3. You obtain a critical, you compute the test statistic. And then when it comes to step 4, remember I said there are 6 steps. Step 4, you obtain the critical value. Where do you obtain the critical value? From the tables, Z table or T table. This is where you will obtain your Z table. And before I continue with step number 4, let's go back to the null hypothesis and the alternative hypothesis. Here, right, you need to know, remember, in most instances, they tell you that this is a single hypothesis testing, or this is a one-sided hypothesis testing is what I mean by single hypothesis testing. So it's one-sided hypothesis testing or it's two-sided hypothesis testing. How do we tell that this is a two-sided hypothesis? You can only tell by using H1. H1 is the one that tells you the tails of your hypothesis. Is it upper-tailed? Is it lower-tailed? Or it's two-tailed? You are only going to look at H1 in order to infer. Yes, I'm sorry about that. Now, listen very attentively here again. Remember, I said for you to identify whether the hypothesis is one-sided or is two-sided, you focus on H1. So if your H1 is saying not equals to, it means this is a two-sided hypothesis. Why are we saying it's a two-sided hypothesis? If we are saying not equals to 2, we are saying the value can be either less than 2 or greater than 2. You see, there are two sides, the right-hand side or the left-hand side. So that is why we are saying not equals to is a two-sided hypothesis test. And when you draw its normal curve, you will have something like this, and then you will have your critical value here, and then you have another critical value here, and then you have your 0. So they are two-sided, you see. And then secondly, we go to the other one. Less than. This one is one-sided because it's on the left. One-sided hypothesis test. And then when you draw its graph, you will say less than means this side. So it's one-sided or lower-tailed. Why are we saying lower-tailed? Because it's on the negative values here. The sign is negative here, the sign is positive here. So lower, negative. So when we subtract, we are lowering that particular value. That's why we are saying it's lower-tailed hypothesis test because of this negative sign here. And then what about greater than? Greater than is also one-sided. Upper-tailed or lower-tailed? Upper-tailed. Greater than means this is its graph. You draw it, it's normal as you can see, and then this will be your area because it's greater than 0 is on the right hand side. So that's what you need to know. And then again, this is what you need to know. There are a lot of things you need to know before we actually go to the calculation. Okay? So this is a normal curve. It's normal, it's bell-shaped, and then it's symmetric. And then, yeah, those are some of the characteristics. And then the area under the curve gives 1. We have 0.5 this side and 0.5 this side. So the area under the curve is the sum of all the probabilities, and then you get 1. So this is what I'm introducing to you. This region, let me say the one that is shaded, is called rejection region. So if you find your value falling inside this region, you must know that it's what? It's a rejection region. It falls in a rejection region, and we are going to reject H0. And then here on this line here, this line, you are going to write your critical value. You write your critical value, and then you also have your rejection region there. So that's what you need to know as well. And then we are continuing. We were on step number 4. Step number 4, we are obtaining a critical value. So the reason I had to introduce you to the one-sided and two-sided hypothesis test is because you need to know, for you to obtain a critical value, you'll be making use of those tables. So if you are using a t-table and your hypothesis is one-sided, you will say Tn minus 1 and then alpha. This is what we are going to use to obtain a critical value for one-tailed hypothesis test. And then for two-tailed, this will be the difference. And then alpha now is divided by 2. This 2 simply tells you that your hypothesis is two-sided. Whereas here, we divided by 1. Anything divided by 1 remains that thing. That is why mathematically there's no need for us to write alpha divided by 1. So you use this one for one-tailed, and then you use this one for two-tailed. This 2 tells you that my hypothesis is two-tailed. Same applies to the Z value. So you use Z alpha or Z alpha over 2. This one is for two-tailed hypothesis test. This one is for one-tailed. That is very important. Make sure you note them as well. And then we are continuing. Something to drink again. We are continuing. Yeah, that's that. And then we now go to step 5. Step 5 is very important as well. This is what happens on step 5. Step 5, you decide. You make a decision. When you make a decision, you either reject or accept H0. We only reject or fail to reject H0. Now, how are we gonna know that here we are rejecting H naught. This is how. You go back to the steps. So if the test statistic is greater than the critical value, you reject H naught. In other words, if the value you got on step 3 is greater than the value on step 4, you reject H naught. We only reject H naught, remember. You will never reject H1, as I have said before. So if your test statistic, which is on step 3, is greater than your critical value, which is on step 4, you reject H naught. Make sure you take note of that. And finally, you go to the last step, which is step 6, where you now make a conclusion. You are going to make your conclusion based on the decision you have made on step 5. So if on step 5 you have rejected H naught, it means you go with H1. So you will interpret your results, or you will conclude based on what? On H1, meaning that H1 works, and then H naught does not work. So that will be your conclusion. So in peroration, or in summary, there are 6 general steps that are involved in the critical value approach to hypothesis testing. The first step is to state the null and the alternative hypothesis. The second step is to decide on the significance level, which is denoted by alpha. If the significance level is not given, you are going to use the default alpha, which is 5%, 0.05. And then on step 3, you compute the value of the test statistic. You calculate the value of the test statistic. And then on step 4, you obtain the critical value. Step 5, you make a decision. You either reject or you fail to reject H naught. And then step 6, you interpret your results or your findings, or you make conclusions. Are we together? So I want us to, I don't know if I have explained everything, but I hope so. I have explained almost everything, the two-tailed and the one-tailed hypothesis test. And then when it comes to H1, if H naught and H1, for example, when you state them, they will say, suppose you are given a mean of 100. They say mean is 100. So your hypothesis will be this. We don't expect to see something like this. X bar equals 100, and then X bar equals not 100. So yes, they will say this is the mean. They will never tell you whether it's a mean for population or it's a mean for sample. But just know that we are estimating a population parameter, meaning that on your hypothesis, we don't expect to see you writing a statistic or a specific characteristic of a sample. In this case, we have sample mean. That will be wrong. We always have a population parameter here. That's what you need to take note of as well. Then I want to go back to my slides before we actually continue. I wanna make that other account a host. Yes. Okay, I'm making this one a host. And then we continue in that fashion. Yeah, I hope you are able to see my slides here. This is what I've been explaining. This. Yeah, I want to go to this. So this is what I was talking about. Step 1, step 2, step 3, step 4, step 5, and step 6. So you need to know these steps. And then I want us to look at the example. They are saying a phone industry manager thinks that, very important, this person thinks that this one here, thinks that. The moment you see things, you know, we are not sure whether that is true or not, right? So meaning that the person is hypothesizing, the person is assuming, the person is claiming. We will need to test that claim, right? So that is a hypothesis. So a phone industry manager thinks that customer monthly cell phone bills have increased. When we say they have increased, it means that they are now greater than they were before. So that is your hypothesis. So meaning that the sales, I mean to say the monthly customer bills, monthly cell phone bills have increased. They are greater than they were before. And now the average is over 52 rand per month, meaning that it's more than, over means more than, meaning that it's greater than. Very important here. It's greater than 52. So what do you think we are given there? We are given mean, right? The average. Remember I said mean is the same as average. Average is the same as expected value of X. Expected value of X is the same as expected value, expected number, right? So you should not forget. Mean is the same as average, average expected number. And then the average is greater than 52. So you go back to the information I gave you. So you will check the signs greater than. They are not saying greater or equals to. They are saying over or more than. More than is not the same as more or equals to. More than 52 is greater than 52, not greater or equals to 52. So which hypothesis are we given there? You go back to the information about the null hypothesis and the alternative hypothesis I gave you before. You will realize that we are given the alternative hypothesis, which is mu is greater than 52, as shown here. You are given this. So now that you are given this, What is its alternative? The alternative for greater than is what? Is less or equals to. And the meaning that your null is mu less or equals to 52. And remember, on the null, we always have an equal sign. And indeed, there's an equal sign here, you see? But H1 does not have an equal sign. It will never have an equal sign. So I hope you understand. We have read the statement, and then we have realized that we are given this hypothesis. The claim is that the average is over 52 rand. So average is mu, is mean. Mean over means greater than, and then 52. And then you check the hypothesis you are given, and then you start working around it. We are continuing. I want us to look at this other example. Oh, yeah, I want us to look at this example. I want to take a picture so that I can present, and then we continue. No, I don't want this picture. I need another one. Yeah, I think this is the picture I'm looking for. Still loading. Yeah. Yeah, let me present. But before that, I need to make myself a host that side again, and then we continue. Yeah, that's a question. That's a question. Yeah, that's a question. They are saying a manufacturer of detergent claims here. No. What is happening? No, I need my blackboard, my live board, not this. This is what I want to present. A manufacturer of detergent claims. The person is claiming, meaning that the person is hypothesizing, right? That the content of boxes sold weigh on average at least 16 ounces. This is a claim. And then they are saying they weigh at least 8 ounces. You write what you are given. And then you are given average is what? Average is mean. And then is greater or equals to. I can't see my screen. Yes, that's what we are given on the statement, right? They are saying the average, this is a claim here, average is at least 16 ounces. Then that's why we are saying we are given mu equals 16, not equals to, but at least 16. They're at least 16, right? And then we go back. We are collecting data. Remember, I said when you read, you should collect data. The distribution of weight is known to be normal with a standard deviation of 0.4. This is population standard deviation. Why? Because they did not mention anything. They did not specify. They did not mention anything about a population or about a sample. They just said this is a standard deviation. So it automatically belongs to a population. So we are given a population standard deviation of sigma is the population standard deviation equals 0.4. What else? A random sample, now they are talking about a sample. A random sample of 16 boxes. A random sample n equals 16. Yielded a sample mean of 15.84. The sample mean, how do we denote sample mean? X bar equals 15.84. 15.84. What else are we given? Test at the 10% significance level. 10%, alpha equals 10%, which is equal to 0.01. My apology, 10% is 0.1. Right? What else? The null hypothesis, they are telling you that what you are given here is the null hypothesis, that the population mean weight is at least 16 ounces. So now we are going to follow those steps, the 6 steps of critical value approach to hypothesis testing. What is the first step? This is what we have, the information that we have, and it will help us calculate whatever they are saying we must calculate. I don't know where my calculator is. I really don't know where the calculator is. I don't know. Okay, let me check this side. It has to be here. Yes. So we start with step number 1. And then step number 1. Step 1. What are we supposed to do on step 1? State H0 and H1, right? Let's state them. The H0. Remember, I said you will always be given a hypothesis. This is H0. So what hypothesis are we given there? We are given this. Mean is at least 16. You go back to the notes I gave you. Which one between H0 and H1 is supposed to have an equal sign at all times? That will be H0. Very good. So it means that we have mu at least 16. You can write in brackets to say the average weight of those boxes sold is at least in width is at least 16 ounces. And then your H1 is actually the opposite of your H0. And then you know greater or equals to, what will be the alternative? The alternative will be mu. Instead of greater or equals to, you have less than. I explained to you how before. Less than 16. In brackets, you will say the average weight of boxes sold is, you can say not at least 16, or you say is less than 16. Here we said is at least because of the sign, and then here we are saying less than because of the sign. And then we are going to step 2. On step 2, this is what we are going to do. We decide on significance level. It's your alpha, and I said it will always be given. This is your alpha is given. You just take it as it is. It will be 0.1, and then you will get a mark. Here you will also get marks. That is step 2. And then step 3, we check, are we estimating the mean or proportion? If you go to the question, they are saying you are estimating mean, right? Meaning that the two tables are involved, Z or T. But then you know the conditions for using T, and you also know the conditions for using Z. So you use T if sigma is unknown and N is less than 30. But this time around, sigma is known, right? Meaning that we are going to use Z. So you will have on step 3, you are going to obtain, or let's say you compute the test statistic. So you are going to use this formula. But before we continue, is our hypothesis one-sided or two-sided? You go to step 1. This is your step 1 here. And then I said H1 is the one that will guide you on whether your hypothesis is one-sided or two-sided. So this one is one-sided because it's less than, right? So it's one-sided. Meaning that we are going to use this formula Z alpha equals, no, not Z alpha, but Z equals X bar minus mu over sigma into the square root of N equals, you substitute. You have your X bar, you go to the data you collected. What is your X bar? 15.84. Right. 15.84 minus your mu was 16 if not mistaken. The mu, this is your 16, and then you write 16 here. And then divided by sigma, you are given sigma, which is 0.4 over the square root of N, which is 16. And then you get the answer. And we said, because of this less than, our hypothesis is one-sided. And it being one-sided, is it lower-tailed or upper-tailed? Less than is supposed to be here. So it's lower-tailed, it's supposed to be here. Meaning that when we compute a test statistic, we are supposed to get a negative value. So you punch your calculator, we need the answer for this. Yes, you punch your calculator, you give us the number, the answer for that. So it will be 15.84 minus 16 multiplied by 0.4 into square root of 16, close bracket. So I got negative 1.6. That is your Z statistic. And then we go to step 4. What are we supposed to do on step 4? On step 4, we obtain a critical value. So the critical value, how do we obtain critical value? We need Z alpha, right? And then there's no way you can get the critical value without knowing this. You must know this first before you can have your critical value. So unfortunately, I don't have that table with me. The Z table, I don't know. Let me see if I can take a picture here. Or I will show you. Let's calculate. The alpha, remember you are given alpha, so we need the 0. Where you see alpha, you write 0.1, right? So meaning that you can take it from here. You calculate. Remember, the Z table is associated with what? With probabilities. So you can calculate the probability of 0.1. So the probability of alpha equals 0.5 minus that alpha. So meaning that probability of 0.1 equals 0.5 minus 0.1, which is 0.4. Right? It's 0.4. And then from there, you can go to your Z table. Go to your Z table. Let me check it in the calculator. I mean to say in the phone. Let me do this. I'm still looking for that table. Where are the screenshots? Is it this one? Yeah, I think it's this one. I don't know if you will be able to see it. Some of the values are not visible. But I don't know. Yeah, as long as 1.9 is here, because I think the answer is supposed to be 1.96, if not mistaken. I don't know if it's 1.6 or what, but we are going to calculate it. Yeah, this is the table, and then you go to your table, this Z table, and then you find yeah, I'm having problems with network. So you go to the table and then you check. Remember, we got 0. What? We got 0.4 as the probability. Was it 0.4? Uh, 0.4. I'm having network problems. Yes, let's continue. I'm having problems with my connection here. Why is it taking time to load my screen? It's still taking time. Okay, thank you. Let us continue. Mind you, we have calculated the probability and we got 0.4. So we need to locate the 0.4 on this table, because for us to get the value of Z, which is this one on top here, we should, not the second row, the ones on top, the ones that are in the same row as Z. So Z, 0.00, 0.01, and also these ones. So these are the values of Z. So this is what we are going to do. You got 0.4, and then you have realized that there are a lot of 0.4s here. So this is your 0.4, your 0.4, 0.4, and so forth, right? So what you need to do, if the situation is like this, you go to where 0.4 starts. So it starts at 0.4015, right? because when you round 0.4015, when you round it off to 1 decimal place, you will get 0.4. And then you are going to compare it with the one that comes before it. Because when you round this one as well to 1 decimal place, you still get 0.4. You only look at these two. The one where 0.4 starts and the one that comes before it. If you check this one, this one, this one, this one, this one as well, even this one, this one, this one, they are many. When you round them off to 1 decimal place, you will still get 0.4. But the rule says, it's not there in any book, but this is a rule. So it says that you go to where 0.4 starts. It starts at 0.4015, and then I want us to write it somewhere. 0.4015. Let me add another page. It's 0.4015. What about the one that comes before it? It's 0.3997. 0.3997. Then after that, you give us their Z values. How do you get their Z values? You check the value on the far left here, which is this one, 1.2, and the one on top, which is 0.08. And then when you add 1.2 with 0.08, you get the Z value for 0.3997. And then the answer is what? Is 1.28. And then you do the same for 0.05. Its Z value will be 1.29. And then now that you have the Z values, right? What you can do is to find the midpoint. We assume that probability is somewhere here, because the probability we got is 0.4, meaning that 0.4 is somewhere here between 0.3997 and 0.4015. So we need to find the midpoint. So the midpoint between 0.3997 and 0.4015. So it means that you add 0.3997 with 0.4015, you divide by 2, you get the answer. So the answer you will get is 0.4. So if the midpoint is exactly the probability you are looking for, you are not supposed to get 0.41, 0.42 and say, I'm going to do what they are telling me to do here. It doesn't work like that. You only go to the step I'm gonna explain after this one, only and only if the midpoint of the probabilities in question is exactly the probability you got. So in this case, it's exactly the probability we got because we got 0.4. So now you are at liberty to add the Z values, you divide by 2. You are at liberty to find the midpoint between the Z values of those probabilities. So the answer will be, so we say 1.28, we add it with 1.29, we divide by 2. And then my answer here is 1.29. I got 1.29. So that is the value of Z for 0.1. So Z of 0.1 equals 1.29. But if you leave it here, you will get your answer wrong, because remember, if you look at the graph I have introduced you before, I said this hypothesis is lower tails, one-sided. Less than means that your critical value should be negative. So you further say equals negative 1.29. That sign is very important. That is step 4. And then you now go to step 5. On step 5, this is what you are going to do. You make a decision, right? So you can decide by drawing that curve. This is your 0. And then we said our hypothesis is lower tail. It's supposed to be here. And I said on this line, you write what? You write your critical value, which is negative 1.29. And then you check, does this answer we got on step 3, this negative 1.6, does it fall in the rejection region? Does it fall here? It does, right? Because you have negative 1.2, negative 1.3, negative 1.4, and so forth until negative 1.6. So your negative 1.6 falls in this region. Therefore, you reject H naught since negative 1.6 falls in the rejection region. That is your decision. So this is a critical value, and then as test statistics is found inside this rejection region. Therefore, we are rejecting H naught. We always reject H naught. You will never reject H1. So the other way to explain this better is to say, remember I said the value on step 3, if the value on step 3 is greater than the one on step 4, you reject H naught, right? So the one on step 3, this is what I'm talking about. If step 3 is greater than step 4, and then you can reject H naught. Are we together? So we are rejecting H naught. But if you can check on step 3, right? On step 3, one might say, but then on step 3, we got negative 1.6, right? And then this one is negative 1.29. So is negative 1.6 greater than negative 1.29? No, it's not. But then by looking at these values, we can just say they are greater than, right? So we can say if we ignore their sign, 1.6 is greater than 1.29. Therefore, we reject H naught. That's the implication there. Now that we have rejected this statement, remember H naught was saying the average weight is at least 16 ounces. So we have rejected it. By rejecting it, it means that we are saying okay, I thought I was kicked out of the session. By rejecting it, we are actually saying we don't agree with that statement. It's not true. Therefore, we are rejecting it. Meaning that when we conclude, we can conclude using the one we did not reject, which says the average weight of those boxes sold is less than 16, not at least 16 ounces. So that will be your decision. Then it's the last step, which is your step 6, conclusion. You say, therefore, we have sufficient evidence to infer or to conclude at 1, it was 10%, not 1, at 10% significance level that the average of boxes sold weigh less than 16 ounces, or you can say weigh not at least 16 ounces. Then that will be your conclusion, and then you get your full marks. Are we together? So that's how we test the hypothesis. Very simple and straightforward. I know something that might have confused you is how to find the critical value using the table. You can go back to that explanation, and then if you don't understand, you can type in your question in the chat room. I'll be able to respond to it. So before I call it a day, let's look at the second example, but we are not going to calculate it. I'm just going to explain how you are supposed to tackle it. But then I will give you more exercises in class, and then you will go through them, and then we will work through them together. We interrogate whatever needs to be interrogated, and then we make our lives easier and simple. So, yeah, I talked too much. We are looking at another example now before I release you. It's been a long day, but it was worth it. Let's look at another example. These ones do not have answers. If you need these slides, you will text me. I will send them to you. I won't be able to send the slides to you because you already have. Yeah, a company that receives shipments of batteries tests a random sample of 9 of them before agreeing to take or to be taken for a shipment. Therefore, you have a sample size, which is 9 here, right? The company is concerned that the true mean, just know that when they talk about the true mean or the true proportion, they are talking about the population mean or the population proportion. True is the same as population. Never forget that. True mean is the same as population mean. True proportion is the same as population proportion. So they are saying the company is concerned that the population mean for all batteries in the shipment should be at least 16 hours. So this is also important. At least, mean is at least. So this will be the same, the problem that is similar to the one we were doing before, because at least will be your null hypothesis. So your mu will be at least. Remember, they are saying true mean at least 50 hours. So if mu greater or equals to 50, that will be your null hypothesis. You know how to identify it. From the past experience, it is safe to conclude that the population distribution of lifetime is normal with a standard deviation. This standard deviation is for population because they told you here. They told you for a particular shipment, the mean lifetime for a sample of 9 batteries is, this is what? The mean, right, of this sample, the sample of 9 batteries, which is 48.2 hours. That is your X bar. Then test at 10% significance level. So is your alpha equals 0.1. The null hypothesis, they are telling you that what you are given there is the null hypothesis. But in the test, they will never tell you that that is a null hypothesis. They will just say, test the hypothesis that the population mean lifetime is at least 50 hours. So at least simply means that it's greater or equals to 30. I mean, say it's greater or equals to 50. And you know, the one that always has an equal sign is what? Is the null hypothesis. So you'll be able to solve that problem, and then you go through all those steps. And then you will also tell whether your hypothesis is two-sided or one-sided. So I don't think you will fail to respond to that one. So yes, we can look at the last one. The accounts of a corporation show that on average, accounts payable are 125. They are saying average. The average, which is your mean, your mu, is 125 rand 32 cents. That is important. This R means equals to. They did not say more than or less than, right? They just said R. So this is mu equals 125.32, but they will tell you as we go further. An auditor checked a random sample of 16, so the value of n is 16. This is the value of n, which is 16. The sample mean, which is your X bar, is this. Assume that the population distribution is normal. Test at 5% significance level. So it means that your alpha is now 5%, which is 0.05. Against a two-sided alternative, they are telling you, but in the test, they will never tell you. They are telling you that this is two-sided. It's two-sided, and you know the one that is two-sided is equals to, right? Must not forget. Two-sided null hypothesis that the population mean is. So if they say the population mean is 120, they are saying mu is exactly or is equal to 125.32, meaning that the alternative will be not equals to. And you follow the 6 steps of approaching hypothesis testing, you solve your problems, you get the answers. So I hope I have said a mouthful, and I am gonna call it a day. So if there's something you are missing, feel free to text me either on WhatsApp, or you can leave the comment in the comment section. I'll be able to respond to it as soon as possible. And thank you very much for attending. Until we meet again in the next class, whereby we will be looking at the hypothesis test for the T value, or when we use a T table, right? Or when the sigma is unknown. So you will see that in the next session. For now, we will call it a day. Thank you very much. Stay safe. Coronavirus is real. Regularly sanitize. Observe social distance at all times. At least 1.5 or 1 point what? Yeah, it has to be 1.5 meters, at least 1.5 meters, if not mistaken, yes. and you must also wear your masks at all times, more especially when you are in a crowded place. So for now, we will call it a day. Thank you very much. I'm going to stop the recording.